just wondering if I am off again. Okay, that should be good enough in terms of the size, right? Again, you guys have this already in your Google Clip. So I'm just going over some of the basic. I've also posted a video feedback concept so that you can use it along with the notes here to help to um, guide you in terms of what is being done and said. And you guys have to give me regular feedback and answers, else I won't know if I am talking to myself because of the pending challenges with the system.
No problem, sir.
Okay. So feedback concept. What is feedback concept? So remember, looking at we said that feedback is a process of returning a portion of the output signal back to the input of a system, and particularly because we're talking predominantly in this class about amplifiers, the whole process of feedback is the process of returning a portion of the output signal and back to the input of the circuit, as can be seen on screen. Depending on the polarity of the signal being returned with the signal that is inputted, the feedback can either be negative or positive feedback. If the signal that is fed back is in phase with the signal that is inputted, then the feedback, that type of feedback is what is known as positive feedback. However, if the feedback signal is out of phase with this input signal, then that signal is considered to be negative feedback. Okay?
Yes, sir. Yes, sir. I mean, that's yeah.
Good. That's what I want to hear. Because if I'm not hearing you, I'm not sure if you're hearing me. All right. So
Because
we have done quite a bit of feedback applications so far in our um, class to date. So what I was saying before is that if you look at, let's say, figure one and this page, you notice that the signal that is being fed back, in this case voltage, you notice the minus sign and the signal that is being inputted, they are combined together, but the signal is positive and the signal is fed back is negative, which means that they are out of phase, right? And therefore,
yes, sir.
we say that a circuit like this, when the feedback signal and the input signal are out of phase, we consider that to be negative feedback. As compared to, let's say, figure 2, where you notice that the feedback signal and the input signal, Vs, are both positive, which means that they're in phase. Now, negative feedback. This is a general statement, no? That negative feedback results in a decreased voltage gain, for which a number of circuit features are improved. So a lot of stuff are improved with negative feedback. But one thing for sure is that the voltage gain of an amplifier with negative feedback, the voltage gain is reduced. And you can understand why. Because when you feed the signal back and the signal is out of phase, it means that the summation of the signal, Vs plus in this case Vf, when they're summed, the, the resulting Vi would be less than what Vs initially was before getting feedback. Agree?
All right. Yeah. Yeah.
And of course, the resultant Vi is less. Alright, so without the feedback, Vi would equal to Vs. But with feedback, Vi is going to equal to, for negative feedback, Vi is going to equal to Vs minus Vf, that is negative feedback,
Yes, sir.
right? And
Yes, sir,
therefore,
yes,
it
sir.
means that you're gonna have less input voltage,
So
which is
VN
going to
is
be
going to always be less than
amplified
VS.
and with negative feedback.
Yes.
With negative feedback, alright? As a matter of fact, the only thing at this level that we need to know as far as positive feedback is concerned is that positive feedback is only used for oscillation. All other circuits with feedback uses negative feedback. And because of that, what happened is negative feedback provides a lot of circuit. Let me let you, Miss Robinson. Okay. A lot of circuit improvements. Okay, so let's go to that page. Some of the improvements that will be achieved due to negative feedback, and I have a list here. Negative feedback will give you a higher input impedance. Negative feedback will also provide with better stabilized voltage. So even though the voltage gain is going to be less, it is more stable. Because and that's one of the thing you want. You want voltage gain to be all over this. Because you don't want to have an amplifier and you're thinking at one instant an amplifier has a gain of 100 or let's say 10 dBs. But in another circumstance, when you have the amplifier in the circuit, really and truly, the gain is only 5 dBs. You don't want that instability. And therefore, negative feedback provides you with this stabilized voltage gain. So you have better stabilized voltage gain. Also, negative feedback improves frequency response. And we'll be looking at some of these in detail. Negative feedback lower output impedance of amplifier. Remember, one of the things that we do know about operational amplifier, especially ideal operational amplifier, is that you want a very high tending towards infinitely large input impedance, and you also want a very low tending towards zero output impedance. So if with negative feedback you're getting an higher input impedance than without negative feedback, then it means that it is allowing your op amp to perform even better. Because ideally that input impedance should have been infinitely large. And also, this negative feedback is providing your operation amplifier with a lower output impedance. Ideally, the output impedance of our operation amplifier should have been 0. So therefore, if you have negative feedback providing you with this lowering of the output impedance, then it means that your operation amplifier is going to be performing better as a result of negative feedback. Also, it reduces noise and it provides you more linear operation. I mentioned already that positive feedback drives a circuit into oscillation, and pretty much that's the only reason you want to use positive feedback for your especially as with amplifiers. So from here on, just looking at oscillation, we'll be thinking that we're talking about negative feedback. Am I clear?
Alright, sir.
Cool.
Oh, wait, sir, oscillation, like the ones, you're talking like the ones that are on the assignment, right, sir?
I'm talking about oscillation, as in oscillators. Yes, it's an assignment, which we can talk about a little later. Let's move quickly into this thing. All right. So for connection show in figure 1. So this is figure one. Come on. All right. So that's figure one. Going back to it. What happened is I probably can quickly, instead of going to one, I can quickly tell you what's in. Now, what happened is that with negative feedback, we can have, well, we know that's a portion of the input, output signal of the input. But there are different feedback connection types that can be, there are four feedback connection types that we will be looking at. And these are voltage series feedback, current series feedback, voltage shunt feedback, and current shunt feedback. All right. So what does all that mean? No. We can feedback a current or voltage from output back to the input. That goes without saying, eh? So it means that if we're feeding back current from the output to the input, then it means that we're having a current feedback network, right? It could be current series or current shunt. If we're feeding back voltage from the output to the input, it means that we have a voltage feedback network. What makes it a voltage series? What makes it a voltage shunt? And like as current series and current shunt is what I want you to pay attention to right now. Again, here's one of the places that student thrown off at time. So jump into the second paragraph here. It said in the list above, the four that I just mentioned, voltage, I wanted to take notes. Voltage refers to connecting the output voltage as input to the feedback network. No. Current feedback refers to tapping off some of the output current through the feedback network. So remember I said it can either be voltage feedback or current feedback. Voltage feedback means that you're taking the output voltage and putting and making the output voltage be the input to the feedback apparatus, a feedback network. Correct. So tapping off. When we say tapping off, we're talking in parallel, right?
Yes, sir.
Of the output current through the feedback network. Now here's what's gonna make a difference. And that's the easy part. We're talking about voltage, we're talking about sending back output voltage back to the input through the feedback network. We're talking about current to take it up, talking about taking off current through tapping of parallel connection, tapping the current from the output through the feedback network back to the input. Well, what makes it series and what makes it shunt? Series refer to connecting the feedback signal in series with the input signal voltage. So easy look at it is that voltage, when we talk about voltage, for example, voltage series feedback, it means that we're taking a portion of the output voltage to make that become the input to the feedback network. And we're talking about series now. It means we're taking the output of the feedback network to be connected in series with input signal. Am I clear?
Separate again, sir.
Repeat, sir. Repeat.
Yeah, repeat that part.
All right. All right. So we're going to be looking at a circuit that will help us. So this is a voltage series feedback. We have the input voltage. You see my arrow? Or do I need to draw on it?
Yes, sir.
Oh, it's alright, sir.
So this is my input right here. That's my input. So the input signal goes into the amplifier. This is the amplifier. And that input that amplifier amplifies input signal and output that signal here. So right across here, getting our output voltage. Okay? Which is the same voltage that is dropped across this resistor. Right here. That's VO.
Yes, sir. Yes, sir.
Still with me?
Yes, sir. Can you hear us, sir?
So like I know I'm not hearing a soul.
Sir?
They were hearing me so well. What happened? Oh, I don't know. I mean, you guys
Sir,
are still
can
there. I
you-
didn't hear you guys. All right. So when we talk about voltage, we're saying that I am hearing you guys. Are you hearing me?
There's a delay. There's a delay, sir. There's a delay. Whenever you hear this, sir, there's a delay. You can't keep going.
Let's go back to this and see what's happening. I am hearing you quite fine. I'm hearing you. I don't know what's happening. You're not hearing me?
Yes, sir. We're hearing you, sir.
Okay. So when we talk about voltage feedback, we take a portion. We take a portion of the output voltage and make it to the feedback network. So this is your feedback network right here. And I'll change the color to show you the feedback network. That's my feedback network right there. This is my feedback network. So we talk about voltage. Taking a portion of the output voltage and making that output voltage become the input to this feedback network. So it says voltage something. So it's a voltage something network. Voltage. Once we take in the output voltage and making the output voltage become the input to the feedback network, we say that this is going to be a voltage something because that is going into the feedback network. What makes it series or shunt is how we connect the output of the feedback network to the input of the system. I've heard that because feedback.
Yes, sir.
Sorry.
Where it is, sir? Just clarifying. 1, 2, 3, 4, 5, 6, 7.
Okay, so
20-second delay.
because the output of the feedback network is connected series. See? In series. So it's not across anything, it's in series with the input voltage. Then it means that this is a voltage dash series voltage series. Voltage series feedback. And that's Facebook, okay? So this is why we say that this network is a voltage series network. A voltage shunt network, on the other hand, is the same connection as in this being fed to the input of the feedback network. But the connection over here for voltage shunt now, it means that the feedback quantity will be in parallel with the input quantity. So this is what we look at next. So in this network, we have the setting where the output voltage happens to be the input to the feedback network. So it's called a voltage something feed. However, notice something here, ladies and gentlemen, that the output of the feedback network is connected in parallel to the input quantity. And notice that the input quantity here is current. Current is the only thing you can connect in parallel, right? Not voltage. The network connected parallel because of how current split, right? All right, so I'll wait for confirmation again.
Okay, so that's 20 seconds. We're going to have to wait. Sir, can you hear us? 20 seconds.
I can hear you. Are you hearing me?
Oh, yes, sir. I just thought there was a delay, sir.
Oh, so the delay has gone.
Yeah, it's gone now.
Good. I don't know. It is raining in my neck of the hood, so that probably could be contributing to the challenges.
More than likely. All right, you can continue,
All right.
sir.
So you guys are good now. Are you seeing clearly the difference between voltage series and voltage shunt now?
I mean, I am kind of, sir, because it's kind of straightforward for the most part. Because voltage series
Good.
is for sending the voltage back, while voltage shunt is in parallel sending the current back.
Absolutely. So voltage means what at the output. What are you taking at the output? To be the input to the feedback network that speaks to voltage.
Okay.
In this case, we saw that we're taking the output voltage to be the input to the feedback network. Series or shunt depends on how you connect the output of the feedback network to the input signal of the network. So if you connect the output of the feedback network in series with input voltage, then it becomes a voltage series feedback. And if you connect the output voltage, the output quantity of the feedback network in parallel with the input or to the input quantity, then that becomes a voltage. Shunt and parallel mean the same thing, all right?
Yes, sir.
Wonderful. Likewise, we can actually look at what current series and current shunt means. Current series, simple speak like that, we're making current now to become the input to the feedback network. And then let me see if I have that on this. And then what makes it so what we'd be doing is stopping off a portion of output current. I might not have a network. Let me see. We're topping off a part of output current back to the input of the feedback network. That makes it current, all right? This is voltage. Let me see if I have a current. And then, based on how we connect the output of the feedback network, connecting the output of the feedback network, we can either connect the feedback network in series. It would be in series with a voltage source. So then it becomes current series feedback. And if we connect the input to the feedback network, we connect current to the input to the feedback network. And then we connect from the feedback network, we connect in parallel a current to the input system, or to the input signal. Then it becomes a current shunt network. So those are the four ways of how we categorize feedback circuits. Now what I want to do within the next 20-25 minutes that we have here to show you some concept that we alluded to are asserted. So remember the 6 parameters we talked about earlier, where we said that negative feedback improves or increases some of the overall performance of a network. Remember I said that?
Yes, sir.
So for example, we know
6 different
one of the things that happened. Right. One of the first and foremost things that happen with negative feedback is this though. of a decreased voltage gain with negative feedback. I want to have high input impedance, low output impedance. So let's look at some of these things. So we're gonna walk or scroll with me now to the proving of some of these concepts. So here, ladies and gentlemen, I can erase this now since you understand what the concept of voltage series, voltage shunt, and so
Yes,
on.
sir.
mean. I can erase this. Into my erase as well.
I think you wrote it, sir. Yeah.
This thing. That's not what I want. Sorry. Here you go. All right, look at the circuit, ladies and gentlemen. And let's analyze the circuit. So we have an input voltage to the network. The network is a complete thing right now, okay? My eraser.
All right.
If my eraser is delayed. Okay. So remember, this is a voltage series circuit, okay? Now, one thing that we have alluded to was that if it's a negative feedback network, which you know these are negative feedback, because remember I said positive feedback, we're not looking at that until we're looking at oscillators. So, negative, we're supposed to get a reduction in the gain of overall gain of a network. All right, so let's look at what's happening here now, ladies and gentlemen. Let's see where. We apply an input voltage, and this input voltage that we apply, Vs, that input voltage, would you agree with me here that Vs is a combination of Vf plus Vi?
Repeat that, sir. If V,
or better yet, Vi is going to equal to Vs minus Vf, as it's a negative feedback.
yes, sir.
Hold on. That's I hope I don't
Yes,
got
sir.
it.
Yeah, let me come back, sir.
Vi is the voltage that is going into the amplifier. So this is the operation amplifier. But this is a general overall circuit that includes an operation amplifier. So VI, what is VI? Okay. All right, do you hear me now?
Yeah.
Okay. So if we should analyze this voltage series network, which if we should analyze this is all of the net. Over feedback. We know that just looking at this network, we know that the gain amplifier. We know what the gain amplifier is. So this is gain of the amplifier.
V over VI.
And we know
right,
the
sir?
gain of the overall network. So this is the gain of the amplifier. Gain of the overall network is 1 junction G's over VS. So feedback. This feedback network super reduce A, which is the gain of the amplifier without feedback. So that's right. So A is V over VI, amplifier. What about the feedback network? The feedback network, the gain of the feedback network, we call it beta. What is coming into the network? Network is VF over VO, which is what I have highlighted right here. Because all I did was just to find what VF was, which is the output voltage of the feedback network, just cross multiplying. And the voltage of output voltage of feedback network is VF equals to beta VO. Okay? So there are a couple of things that we know so far. Remember, this is what we're trying to do. On the overall gain, which is VO over VS. All right. as far as we're concerned, no feedback, we would get amplifier would just be simply VO over VI, which means that we can find out what VI is, because VI cross multiplying VI is VO over the gain. We can find and highlight what VF is. Because VF, as I said, is beta V, is gain of the field. Okay? So, here, a couple of minutes. We said that this without feedback. We said also that the voltage out the network is beta VO, because beta equals to VF over VO. Okay? There's something else we know. We know that VS, right here, VS equals to the feedback voltage F plus A. We know that. Just by looking at because VS is going to be in this as feedback with what is here. So this gives you this. Okay? And if we know that VS equals VF is VI, then it means that we can find from this expression VI. VI is VS minus VF. I am very much here.
All right, so I was just checking the day.
All right. So we say that VI also equals VS minus VF. Because we know what VF is, we can put that into this expression to make VI equals to VS minus beta VO. But we also know what is VI plus VF. We know that. See, VS equals to VI plus VS, which is what we have here. So, if that's the case, we can write what VS is in terms of what it is. We said that VS equals to VI plus VO. But we know that VI, this is VI. We know that this is VI. And we know that this is VF. It's too big. We know that this is VF. If VS equals to VO plus beta VO, that's what VS is. So we can start out VO because we have VO in both sides. So VO equals to 1 over A. This is VS equals VO into 1 plus beta over A. That's what VS is. Okay?
Yes, sir.
And what were we trying to find again? We were trying to find network over V. For VO, all right, VO, which equals to, sorry, the gain, the overall gain is VO. I hate using this eraser because even that is delayed. 12. That's for the gas from this one. I didn't bother using. So put it in the tip one. I'm gonna have to follow the gas tank one. All right, I hope my delay is on and you guys are with me.
Can you hear me, sir?
So this is what we're trying to, we know what VS is already. So we're trying to find VO over VS. And we know that this is going to be VO over what VS is? VS is this, which is VO. I can hear you into 1 plus beta A over A.
Oh, just say no, sir. The delay gone up to like 36 seconds or so.
So therefore, mathematically, we can see that this now will equal to 1 over 1 plus beta A all over A. No. So that I hear that's what VO over VS would be. And from math, we can simplify this to become just to flip it. Because it has 1 over all of this, it means that this become that VO over VS is going to become this by flipping it. And you can see clearly that the overall gain of the network is going to be reduced. Because if A is the gain of the amplifier, and you're dividing that by 1 plus beta times A, unless beta times A is 0, which is highly unlikely because A is not 0 and beta is not 0. Because if beta was 0, it means that you would not have had a feedback. So it means the gain of that amplifier is reduced because of feedback. And likewise, we can do that also in this voltage shunt network until you acknowledge me.
Okay.
And
I hear. You cut up the as in where we are now.
I'm just hearing you know, so hopefully the rest of people are confirming their understanding as well.
Yeah, man, sir, we're here. We're understanding.
Okay. The ladies are quiet tonight. I don't hear the ladies talking. They said cut that. Well, can I go ahead, but that's it,
Go
consent.
ahead, sir. You stop. Yes, sir.
Okay. So I delay gone again.
Yeah, gone.
Yes, sir.
All right, so you have a little bit of voltage shunt feedback, right? That's the circuit on screen.
Yes, sir. Feedback connected in parallel.
So we just put that for the voltage shunt. My apologies. For the voltage series, we just prove that gain of a network with feedback. The overall gain will reach. Well, that's for the voltage. Let's look at that. So observe the record carefully. Now, I want you guys not to panic, but just to take it as that the gain of a network is the output quantity over its input quantity. Is that correct?
Yes, sir.
All right. Now, what's the input to this network?
The IS, sir.
Very good. What's the output of this network?
VO.
Very good. So what's the gain?
AF over VO.
Sir, I think maybe you want to take it in terms of current, sir. So we put IS over VORL. Or is that wrong?
Okay.
V
Let's go
over
on.
IS.
The gain for which one, sir?
Simple.
Because the overall circuit is, I think,
overall
over
I
IS.
say it, you know, I said, let's take it as is. And I went through the process and you agree with me that the gain of a network is the output quantity over its input quantity. You guys agree with me? And then I said to you, what's the input quantity of this network? You told me that it was IS. Okay. I said, what's the output quantity of this network? You told me it was VS.
The VO.
And then I ask, what's the gain of the network?
VO over IS.
Absolutely.
Yes, sir.
Don't watch the units, right? The variables right now.
All right, sir.
Just put that the gain network with feedback is VO over IS. Now, you know, there are a couple of other things. Would you agree with me that IS equal IF plus II?
Yes, sir.
Would you have that from what is of the over II? Oh. Yeah.
Yeah.
You can say II then would be what? We can express II or we can express the gain. Doesn't matter. We can say the gain of the amplifier. In this gain of amplifier, sorry, always I. Am I correct?
Yes, sir.
So okay, we can do a couple of things. We know that the overall gain of the network with feedback is going to be this. But we also know a couple of things. We know that VO from what we just discussed, VO, this is VO. And I just mentioned that IS, which is these two currents that are summed, it's going to be II plus IF. So it simply means that we can express this as II over I, so I times or II plus IF, which means that, well, we can actually write this as is again, because guess what? IF, which is the current feedback, really beta times VO. That's what IF is, right? The IF is the output for the feedback.
Yes, sir.
IF, based on this, is going to be beta VO. True? So this is IF right here. That's IF. So just basically writing back what we know. This is IF. This is VO. We know this is VO. We're writing back this as VO. But we know that this is VO, and we have a VO here. So we can put what VO is in terms of I. So that's what we do it here. We make this be VO. Because we know that that is VO already. So therefore, we have this expression now, which means we can actually factor out out of the denominator to make this become what? AI oops I should say AI over factor I out of I into 1 plus what? Beta times A. Beautiful. But it has
Yes, sir. Yes, sir.
No, we good, sir. Good, sir. I'm on the lead, man.
you guys still me?
Yes, sir.
Like, sir, delay again.
A wiki 30 seconds or something.
So mathematically we can then just say this, cancel this. Then that would leave you with this. Delay. I think it could be because of the rain. You know? For Marcos. Hello. Are you?
Yes, sir.
Yes, sir.
All right. So like delay God again. I was just thinking saying that
Delay gone again.
Uh, the trim comes with
based
trim.
on that whether or not we have voted Sean or voted series, the gain of the overall network is reduced. And it's reduced by the same factor, 1 plus beta times A. All right, so that's one of the things that we had suggested or alluded to, and we are now able to mathematically prove that from our analysis, show that that is actually the case. That with feedback, the gain of an amplifier, the gain of a network with an amplifier is reduced. All right, I'm look at 1. network to show you how the input impedance. Remember what I think I said? The impedance, I know, or 6 things that I said earlier was that the input impedance is improved with an amplifier that has negative feedback. Here we have a circuit, and this is our circuit again of our voltage series network. When it was voltage series, voltage that we're applying, having voltage here as what is coming to the feedback network. And we have a feedback network output in series with the network. But there are some things that we know also, and that is this remains the same, that VF is the output voltage for the feedback network, which is beta times VO. We know what VO is. VO is VO. That's coming from this network. This is the amplifier, internal part of the amplifier. And the amplifier has an input impedance. We know ZI. The amplifier has an output impedance, ZO, which should be low. And we know that, and the gain will give you the output voltage, where the output voltage is going to be taken as is V equals the gate impedance, which we have here. That's output voltage, right? And that's all inside of the amplifier itself. But overall, this is the network itself. The network has an input voltage VS. VS will supply a voltage which will cause a current to flow. Now, the overall network will have an input impedance, which I call ZI prime. And what we want to find is what's the overall input impedance of this network. That's the whole objective. We want to find what is ZI prime. Mathematically, we can prove that. We know that since this is the input voltage and this is the input current, then the input impedance must be the input current over the input voltage over the input current, right? Right?
Yes, sir.
There again. Good. So that's what we want to prove. We want to prove that the overall input impedance ZI prime equals to VS over VI. Example. We realize that I is the only current that is good the amplifier. So I will equal II. And there's no other current that we're thinking about. What just thinking about the flat voltage. But because it's a series circuit, we know that circuit is one current that is going to flow in a series circuit. Right? and that is in this case I. Input side, IS, sorry, on the input side. So IS will equal to I. Agree with me?
Yes, sir.
Yeah, man, sir.
Good. Would you agree with me also that, and we did this already, that VS equals to VI plus VF? Yes equals to VI
Yes, sir.
plus VS.
Yeah, man.
VI plus VF. Okay. Cool. But we know what VF is. Because we can look right here and we see what VF is. So we can put back into the formula. Ay, 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 ay. Anyway, say VF, this is VF. VF equal to VO times beta. So we can put that back into this formula. VS equals VI plus VF. But really and truly, VS equals VI plus beta VO. Agree?
Yes, sir. You can keep going.
Okay. Right. So since VS equals to that, we know what VS is. We can write it back. I think it's already now, but let's write it again. Write back as VI now plus it my beta VO. We could write that because we know what VF is. All right. But that's VS. And remember, our objective all the time is to find VS over VI. So II. VS over II, the same thing as VS over IS. Because remember, II equals to IS. So it means that we could do this. Could say then that this is our objective. VS over IS, which is the same thing as I. Because IS equals I, which then means that we could write this all over II. Agree? And if that's the case, it means that we tell them that this really, which is Zi, remember that this is Zi prime. Zi prime is VI over II VI over II plus beta VO over II. And really and truly, coming back over here since I don't have more space, VI over II is what I have here, VI over II, is really ZI. Agree? VI over II, ZI. And VO. What is VO? VO is AVI. So then we could actually write it as ZI plus beta over VO. But remember, we know what VO is. VO is AVI from here. So we could write ZI plus beta for AVI over I. And if we simply just write, we can simply separate this. Because this by itself, again, from we know already, VI over II is also Z. So what we're going to get is ZI plus beta AZI. And we can factor out ZI. So it becomes ZI into 1 plus beta times A. So that's what ZI prime. So we see that the overall input impedance for a network with feedback is going to be ZI, which is the original input impedance of the amplifier, but that's going to be multiplied now by a factor of 1 plus beta impedance for a network with feedback is going to increase, which is one of the things that we had alluded to, that an overall input impedance is going to become higher. So that's what we have proven right here. Seen it? I delay.
We see, sir.
All right. I'll give it tonight. Because the rest are simple proofs. Again, show it. Again, input impedance, whether it be for put series or voltage shown, inputs are something. Which is what is showing you again right here. Other thing that on this is for you to and prove the others. I want to look at them and look at the proof. It's an important thing to read. So these are the proof. But there's an important thing that, and this is that session. We're going to improve a reduction in frequency distortion. You're going to have a reduction in frequency distortion when you have a network. It's very simple. If the feedback network is purely resistive, or if it is not purely resistive, what will happen? And I can tell you easily as a summation of this that I want to read. Remember, we've been looking at feedback networks in our application so far. For example, the invert amplifier, non-rate amplifier, summing amplifier, difference amplifier. All of those that we have looked at so far, we have had pure resistors in the feedback network. But we look at networks such as integrators. We realize that the feedback network is not purely resistive. And a network that is not purely resistive has the tendency to increase distortion because a pure component such as a capacitor does, they are frequency dependent, right? That's what XC equals to 1 over 2 pi FC, and XL equals to 2 pi FL. Which means that they are frequency dependent. So, for those network that has frequency dependent component as a part of their feedback network, those network will increase frequency distortion because frequency is going to be developed across those components and negatively impact, as it relates to distortion, negatively impact the performance of the network. But if you have a network that has pure resistive components in their feedback, if you have a circuit that has pure resistive component in their feedback, because resistance are frequency dependent, it means that those networks with resistors only in their feedback as their feedback component will not be subjected to frequency distortion because they do not depend on frequency. There are no frequency dependent component in their feedback. There? So that's what this is telling you in a nutshell. And then finally, we said that the output impedance of amplifier with feedback is going to reduce. Which is what happens in the next, next page. Come on. Are you guys still there?
Yes, sir.
Yes, sir.
All right. So what is done in this portion with output feedback, which I want you guys to go over on your own, because I've gone through the other already. So all you have to be doing is just looking at the output. How does we assume as one of the 6 stuff that the output impedance is going to reduce with negative feedback circuits? That's an assumption, but here's the proof. And I've done the proof for you. I just want you to go through the proof and see how it comes up. So at the end of the day, you see, the output impedance with feedback. That's what this means. Output impedance with feedback. Eventually, when you do the proof, and it's just a couple of line proof, you see that the output impedance actually is reduced by a factor of 1 plus beta, which means that the output impedance is gonna reduce view and feedback as compared with field. And then what I've also did is to give you a summary of the quantity for each network. So voltage, series voltage, shunt current, series current, shunt. What's gonna happen? Impedance, output impedance, right? So here, for example, input impedance for voltage, when did that it increases and so on. That's also a summary of the table and an example for. Instead, ladies and gentlemen, a video that should help you with some of the concepts that I've explained here in the Google Classroom. So if there are no questions for me, I again must apologize for the technological challenges that we've been having tonight. Circumstances beyond my control, but I hope that at least you'll be able to follow, okay? Thank you for your patience.
Sir?
Yes, sir.
Yes.
So I just had one question, sir. For
Yes.
for A and B, sir, where it said develop the two-port impedance model. I wanted to just know if it wanted like us to redraw the circuit in those models, or if it wanted the parameters.
Okay.
It's just for A.
It's very clear. What happened is that you have a circuit, but if you notice, the circuit actually has two circuits really together. You have a voltage divider network that also have another circuit, I think, at the input, which is the voltage follower. And what you're going to do is to develop the overall two-port network for that composite circuit that you would have been given. But to do the analysis, what you're going to have to do is to look at the two circuits independently, knowing that the output of one is the input to the other, and see how it is that you can come up with the overall two-port network for this particular circuit. Okay?
Yes, sir. I was looking at the circuit. Okay.
It is a challenging circuit to analyze, but a lot of it the e-copy of the textbook.
Oh, yes, sir. Yes, sir.
Miss Campbell, are you there? Guess not.
Thank you. Thank you again, sir.
You're welcome. I just wanted to share with Miss Campbell, and I think I did from the inception of the class, that most of your students would have had the e-copy of the textbook, so she needs to get a copy if she hasn't already, which should help her with some of these things that we're doing. All right, guys. Make sure that
I'm
you
sorry,
upload
what's the
it
name
for
of
me
that
as
textbook?
that's
It is, sir.
it is. Oh, you disappeared. What's the name of the textbook? It's electronic device and circuit. It's I Robert Boys and Neshelsky. That's right, boys. Yeah, so then, just ask one of the guys, one of the girls in the class, they should have soft copy that made it available. They should be. It's
Feel like I'd already know it. I'm just going to double check.
all right, there you go.
But if anything, I will ask somebody. Sir, I'm actually in the only class. So for me, it was actually uploaded this week. I didn't realize that you had uploaded it for the other people before. So can I just submit with the class that I'm a part of?
Yes.
All right then.
All right. Without further ado, let me wish you guys good night and a good weekend. And we will meet again. Please pay attention to the Google Classroom because there are constant information that I'm always trying to find that will help to make topics a little bit simpler. Sometimes it might not necessarily be in our native tongue, as in there's an accent with it, but if you listen carefully, it's in English. You'll be here, you can hear the things that are being said. And of course, those are just additives to what I would have provided in terms of notes, slides, PowerPoints, and textbook. The next time we meet, we'll be looking at frequency response of an amplifier.
And could you go for the assignment as well, sir?
We could. Actually, after you guys post up all your answers, I submit all your I will actually even post the working note in the classroom. So nobody after that can actually submit because they're gonna get a 0. That's how serious I am.
I mean, sir, can I at least give them like a 2-day grace period, sir, then, if that's the case? Because I know, say, some people, we're not too sure about them Wi-Fi and them stuff there.
Okay.
But yes, sir, the answers would be nice.
Yep. Also bear in mind, as I said before, we're gonna be looking at frequency response of an amplifier. And that is also in the Google group. So we'll be looking at that next time we meet. All right.
Yes, sir.
Take
All
care,
right,
guys.
sir. I
Good
found.
night.
I just wanted to make sure it was the right one.
Okay. All right. Peace out. Have a good night.
You too, sir. Good night, sir.